Welcome. So this question says a spring and block system oscillates with simple harmonic motion. The spring has a spring constant of 8 newtons per meter. The block has a mass of 32 kilograms. The block is displaced 3 meters from equilibrium, then released. What is the period of the system after the block is released? So let's just have a quick draw of it. So here's our table. And we have the spring and mass system like this. And here's my equilibrium position. And here we are 3 meters to the side, and we'll let it go. And it oscillates backwards and forwards. So this is time down here. And we're starting off from the right-hand edge and going backwards and forwards. What do we know? Let's do our table of things. So we can say that K is equal to 8 newtons per meter. That's the spring constant. We can say that the mass of the bob M equals 32 kilograms. And we can say that this maximum displacement, the amplitude, is equal to 3 meters. It's 3 meters because we move it to the side 3 meters and then we let it go. That's basically, from a visualization point of view, it can never get further away than that 3 meters. So that's a way of telling you the amplitude without actually using the word amplitude. And then we say, what is the period of the system after block is released? So we have T is equal to. So there we're at it. I need to get a relationship for this, and I don't remember every relationship that's in the book. What I do is I remember key relationships. So I know that the angular frequency is equal to the square root, and it's going to be of K over M. And I also remember that the angular frequency equals 2 pi f. And I also remember that f is equal to 1 over the period. If I put these two guys together, I get that omega is equal to 2 pi over the period. Well, if I take this first omega and this omega, I can easily see that 2 pi over t is equal to the square root of K over M. And so rearranging, I can see that T is equal to 2 pi, the square root of M over K. And I can stop for a second. And I can say this T is the time it takes for one complete oscillation. It's this time period. And so it's a good idea to stop now and say, does this make sense? If I have a more massive block, it gives more inertia to the system. And so what I would expect that as the mass of the block increases, so the period increases. And that's what I found. And this K is the stiffness of the spring. Big K means a stiff spring. Low K meaning a soft spring. If I make this K stiffer, if I make it a bigger number, I would expect this thing to oscillate much more frequently and therefore have a much lower period. And as K gets bigger, T gets smaller. So that's a good sign. That means although I didn't remember this equation, it makes sense to me. And then the other thing I can do, which is very useful occasionally, is I look for analogies. And I just, from, bygone days, I just got drilled into me that the period of a pendulum is equal to 2 pi root L over G. And I can see the analogy with the form. So all of these things let me know that I've developed the right equation, even if I didn't commit this exact equation to memory. It's your choice. You can learn every equation in the book, or you can basically learn fundamental equations and practice just deriving more complicated things from the simpler equations. However you do it, we get to the stage where we have the equation, and then we say, well, t is equal to 2 pi, the square root of my m, well, my m is 32, and divided by my k, and my k is 8. So this will be 2 pi times the root of 4. So t is equal to 2 pi times 2, which equals 4 pi seconds, and pi is about 3.142, call it 3, about 12 seconds. It's going to be about 12 seconds for one oscillation. 32 kilograms is a massive mass. So the number makes sense. In my tests, I don't mind students, in a test, because I ask a lot of questions, I don't mind students leaving things in pies occasionally. I'm very clear with people. When you can leave a factor in like this, or when I want you to work it out. But it's not uncommon as physics progresses that people can leave constants in. So there we have it. It's approached in the same way we always do. We do a diagram. We make a list of what we know and what we'd like to find. We use that list to stimulate our memory and think of different relationships. We're looking for the relationship which links the things we know with the thing we don't know. And then the math actually is less significant than many people think. It's just numbers at that stage. So there we have it.